that's what we're doing here in San Antonio with these three companies as support XR and Wex Foundation. And I'll talk a little bit about those three companies first before we go into the space landing pad topic. Yes, it is. So a little bit about what space architecture is. XR was a company I founded in 2007 when NASA was going back to the moon back then with a program called Constellation. And it didn't happen. There was funding and all kinds of issues that occurred. But I was positioning the company to start working on the lunar surface systems architectures. When that didn't happen, I migrated or pivoted, that's the word I use these days, to terrestrial space architecture. And I'll tell you what that is in 1 second, but let me give you about the 3 domains of space architecture. The first one is in planetary surface systems. How do you build on different planets? How do you build habitation and settlements and the site plan that goes into living on another planet, essentially, from an architectural perspective. The third domain is an orbital architecture. That's how do you live in space itself and orbiting space stations. And how do you design for that for habitability for crew members, crew quarters, galleys, that kind of thing. Those are how the architects fit into that part of it. And then the third one is terrestrial space architecture, which is what we do here on Earth to support the spacefaring activities, such as spaceports. And that's what we pivoted to back in 2007 to designing these commercial spaceports. The one that Virgin Galactic's Richard Branson's vehicle flew off from in New Mexico. Well, we were part of that design team that did that spaceport for them. We also worked on the Houston spaceport, which is now a robust spaceport with lots of tenants and activity going on. So we looked at all that and decided that we have this background in space landing ports and all that. So that's why we moved to the lunar surface of it. We think we have projects in all 3 planets. As we say, we think we're interplanetary space architects because we work on all 3 planets, essentially. Here are some examples of the studies and the designs we've been working on for the space terrestrial piece of it. I mentioned this Virgin Galactic, Houston Spaceport. Our current project is with the U.S. Transportation Command. This is the command that transports Victoria Island personnel across the globe to forward deployments and expeditionary force. We're working with a program they have called Rocket Cargo, where they want to deliver cargo, 100 tons of cargo in under 2 hours of time by point-to-point rocket transfer. This is Elon Musk's Space X Starship program, where he wants to do that commercially. And our role in that is to understand the ground transportation piece of it, the logistics. What's the implication of getting a rocket in a distant location where there's no infrastructure, there's no support structures, and how do you get it back? Our role is to figure that part of it out. So this is an ongoing program. And the idea is to integrate that into the other modalities of transportation, airlift and sea lift. So now you have space lift happening. So that's that's a little bit of what XARC is doing. And in the Wex Foundation, we work with some NASA money that they gave us a good chunk of money to make a program here in San Antonio called LCATS, which is Lunar Caves Analog Test Sites. It starts at middle school, and we have them through high school, and we teach them about learning to do scientific measurements in the field. And in the field means going into caves. So they build their science instruments. We take them to caves here locally, and they explore the caves as an analog to a lunar lava tube, essentially. And they learn how to take the measurements and how to build robots and understand the implications of doing teamwork and working inside and in the field as a scientist as well. The other program is a national program called New Worlds Await You, and this was established in space clubs around the country. We have 27 schools in about 13 states, and is targeting a different type of student, also middle school, but these are at-risk students that are at risk of dropping out. The LCATs are targeting students that are more motivated to STEM education. Here we're trying to get them into a STEM motivation. And we just announced last week our national competition to how do you design a habitat in the lunar lava tube. So the teams are going to be coalescing around that theme and providing us their designs for habitation in the lunar latitude. So we're real proud of this. I'm really happy about this program. This foundation has been real successful. So the third one is what we're here to talk about is Astroport, and we're looking at building lunar infrastructure. Essentially, how do you build lunar infrastructure? Now, going back to the moon, what do we know about that? We know that there's a human initiative to get back there permanently this time, not just boots on the ground and go back, but to stay there and establish a base, an outpost, and research, and even the mining aspect. By 2026, we'll have the first human man and woman on the lunar surface, and then from that point on, they'll start building up the infrastructure and building up the capability to go back and forth. But what do we know about getting there, though, and landing there? So the issue is, when you land, it's pretty dangerous. It's a harsh environment. You have uneven terrain. You got dangerous plume blasts from the rocket itself. When the rocket lands, it ejects all this plume out, and sometimes at such velocities, it even goes into orbit around the moon. That becomes dangerous when you start thinking about multiple spacecraft coming to the moon. And you got ground debris as well. So our solution to that, of course, is the that's the answer. No. There we go. No, one too many. Well, okay, that's the next one. All right. So our solution to that is using the resources that are there. I mentioned the negative impacts of lunar dirt, the debris and the plume blast, and how dangerous it is, and it's hard for even the work in there with machinery, and even you don't want to breathe this stuff. But it's also got a good positive side. The lunar regolith, the soil that's on the lunar surface, is called regolith. It's a resource, and we can use it for solidifying, making building products out of it. We can even extract metals and minerals out of it for additional products that can be used, and even get water out of it and oxygen out of this dirt. This what you see here is a simulant. We work with simulants that the basalt. Essentially, the majority of it is a basalt material, and we work with this basalt material that we source here locally in Conifa, Texas, as a mine there, a quarry, and we can use that to work with our research and the experiments we're working on. How do you do the solidification? How do you do the extraction? And to do that, we wanted to use that for the ability to do the infrastructure, the construction of these landing pads in the first base. So the first thing you got to build when you get the idea of going back there for a permanent stay, you have to build a landing pad, because you need to be able to protect the assets that you maybe have put there in the first landing, two or three landings. Don't get blasted away by the plume blast and the ejecta, and they'll be destroyed. So you need to have these safe landing locations, and our goal at Astroport is to provide safe landings on the lunar surface. So what we do space materials investigations. This is a picture of Alan, I think, in his laboratory. Alan, his lab is a partner with us in this research. And they're doing the rheology and the understanding of the melts. We're doing the space construction part of it. How do you take that knowledge and turn it into those hard materials? How do you actually place it? The 3D printers need to be used for it. And how do you construct it? The robotics that have to be used to take what you've built or been able to create and make it into a useful ability to print down onto the surface. Then our ultimate goal. This is probably about a 10-year research and development effort here of understanding those technologies, and there's no market for that. Okay, there's no market in that time frame, and as a business, we have to be able to sustain ourselves. So our goal is to look at this over this 10-year period, this long lead time, mature the technologies so that we are able to get to the surface and start operating the landing pads as an operator. So we don't only want to just be materials and constructors. We want to be operators of the pad, and we, as an operator, would be able to charge landing fees and maintenance fees and refueling fees as well. That's the business model of what this company's about as well. It's a long-term vision. Okay, we think in 10 years we can get there. So what are our competencies and technologies? We're refining technologies. We're building furnaces, lunar furnaces to do the melt. How do you melt this regolith? There's all kinds of ways of doing it. You can melt it, you can sinter it, you can microwave it, but we're focusing on melting because what we want to do is not have to be able to rely on imports from Earth, such as binders or reactive agents, to help solidify the regolith. And if we can figure out how to make it just purely out of the regolith, which is what you see here in this picture, we've done some first brick tests, coupon tests. We've been able to do that. This material is harder than concrete. We tested it out to even strengths that show that it competes robustly with concrete. And then we want to get into building the rods, and tubes, and the connectors as well. There's other products as well. They call rebars. What's called rebar. And then we have a way to place it. We have a proprietary technology that is a way to 3D print with the nozzle these bricks. And then we have also the construction aspect of it, which is the mobility robot and the construction excavators that we need to have to acquire the raw material. We have to prepare the pad by doing the site preparation, which is excavation and leveling. But all that dirt we're digging up can be used for our source material for the melts to make the tiles, the bricks. And these are just some examples of some products that we can get out of this. Okay, we do the excavation, we can turn it, do the filtering. We do the melting, we can pull out with this furnace. We can pull to make fibers, basalt rebars. These are goals at this point in time. We're not there yet. We're only at the brick stage. Okay. And as we go forward, continue, we can even get into, we're looking at glass surfaces, reflective surfaces as well as a possibility. And here are some examples of the rods we've been able to apply as well. So it's a very nascent research. Okay, at the beginning of it. This is kind of the bulk regolith aspect of it. Easier one to tackle. The other ones might be a little bit harder. Okay, but we'll get there. Okay, it just takes money, funding. So, and we're on a good track with NASA to do that. They've been real happy with us so far. We just had a contingent of NASA folks come yesterday, about 9 of them, to come look at our labs and see what we're doing. I think we're on a good roll with that. All right, so here's we received some money from NASA to what's called a STTR award, together with UTSA, to combine our furnace with this nozzle. The goal is for them to get integrated, the nozzle and the furnace, so that we able to pop out these bricks digitally. That's what the idea is, to put these bricks down one at a time, and they form this landing pad through this robot. We're currently at the stage we're able to do prove out the bricks, but now we got to show that we can do it in a vacuum. We have to make these bricks in vacuum. Okay, that's been a bit of a challenge for us. Now we're probably a month behind schedule because of some supply chain issues and other things that go into the mix of the design of the gantry and the printer that has to go inside this vacuum we bought. But we'll get there too. I think we'll be there in about a month or so. We'll be able to show that we can make the bricks in vacuum as well. So the way we're doing it, you see how these are individual tiles, and part of our method here is that the nozzle comes down and prints one brick, and it goes to the next spot. It lifts one side of the nozzle, so it's an actuated nozzle, puts down the next material to form the brick, and the form work of the location where the brick is adjacent to the first brick becomes the form work of that second brick, and so forth. You put the third brick down, 2 walls go up, and now you have 2 walls that are adjacent here and here. Those 2 walls go up, and the formwork, okay, is formed by the bricks themselves. That's the way and the reason we want to do this is because if we were just putting down the tiles themselves and had grout and mortar, the rocket blast will blast it apart. Okay, the air entrapment will get inside in between the cracks and whatnot. We want to make a cohesive surface, flat surface. So that's kind of our secret sauce into the way we make these tiles. So to do that, then we need a platform, mobility platform. We're talking with I don't know if you're familiar with a robot called Athlete. It's out of JPL. It's been around since a good 10 years, but we're working with them to see if this is a good platform for mounting our or furnace on with the hopper and all that. And the issue is going to be, what's the design pattern? How do you spiral out from the inside out to go out with the bricks? So how do you come into it? What's that print pattern? Because you don't want the wheels and everything else on top of the bricks you just made and like that. So those are another challenges. Then we have another robot we're working with that might not be that one, it might be another version of it. So here's a little movie, I think. Let's see if I can play that. Is it playing? No. No, it's not playing. Yes. What was the problem with movies?
Is it embedded?
Yeah, it's embedded. It should play. No. Well, I guess we're not going to see the movie. So anyway, it was just to show you the kind of the sequence of how it turn out. All right, so let's talk about the landing pads themselves. When you design a landing pad, you have to deal with what are the rockets that are going to, what are the landing crafts they're going to be landing on it. And NASA's chosen right now 3 companies to go forward with the design of the human landers. There's also a cargo lander, which is what this one is. SpaceX won that contract for the first demonstration mission to go and land on the moon. The other 2 have won subsequent contracts with continuous studies for the actual service. There's going to be a competition for who's going to, out of the 3, who's going to be the one that's going to be chosen by NASA to deliver humans to the moon. So far, SpaceX is in front because it's going to be a demonstration mission. But there's going to be a company that's going to be chosen to be the one that continuously go back and forth with the resupply missions and crew as well. But I believe all 3 of these companies will be in the game in one way or another, because that's not just NASA who's the customer. There's a whole commercial ecosystem being built right now. This what they call Space 2.0, commercial companies going back to the moon. We're not relying on the government anymore. There's a business cases for mining and extraction of minerals and ores and whatnot for the commercial ventures. And then there's the cargo delivery as well. So you have to understand, we have to understand what are the requirements of these landers when they land on that pad. What do we build the pad to in terms of the strength and the bearing loads and the way it interacts with the rocket engines. And one of the first things is, what's the size of the pad? What's the diameter of the pad? Right now we're thinking we're from 50 meters to 80 meters in radius. We have the offloading zone, the middle zone, the target, really what they call the blast zone. And then after that, there's a blast zone radius where in case there's an accident, the blast will not go any further out if you have protective barriers around it as well. And then of course this is where you have vehicles traversing it, doing the offload and whatnot. So we think we have to build a pad around this diameter at the most 80 meters. I'm sorry, radius. And it might not be the same material as those bricks. It could be a less material or maybe a softer material, but the hard core material is going to be the one in the middle of the grid here. And you have these requirements here. You have the landing pad requirement itself. It's the load radius, the resting load itself, the blast radius, as I mentioned, the stagnation temperature. After the engines are cut off, there's some activity that occurs that could be interacted with the other engines. And then there's plume velocity. Then you have the lander properties themselves of the lander, the struts, how many struts do they have, how many engines they have, the location, the landing mass. All that's got to go into the requirements for how we strengthen our material, and construct the pad so that it withstands the landing, but not just one landing, but multiple landings coming and going and launches. Because some of these concepts are 2-stage. Where you land, there's a descent and ascent stage where you land, and then the ascent stage, when you're done with your stay, you take off, but you leave behind the descent stage. That stays on the pad. Well, we got to get rid of it, right, for the next landing. So those where do we take? And that's going to be valuable material, as a matter of fact, because anything you bring to the moon is gold. Whatever you bring there, it's going to be reused and recycled. Talk about sustainability. The moon is the ultimate sustainability objectives. We can reuse all that material in some form or another. And that goes back to our melter or furnaces. We can melt down that aluminum, melt down those metals, and then reuse them and fabricate them. All right, so here are the elements that go into into our construction, the way we've been designing this pad. We have the site preparation tools, which are all the excavators and the compactors and the sievers and the levelers. We want to sieve out the first bigger rocks and boulders, get them out of the way first, and then come in with the excavator, and then we use that for additional leveling, but also for taking that soil and dumping it somewhere else so that we can use it for our tiles. And then then you level it out and you can compact it down in soil so you have a surface that you're going to print your bricks on. And then you have the production itself, which is this, of course, this is the brick layer we talked about. This is the device for that. And then you need the land and blast shield itself. So we have another concept for bagging the soil up. We call RegoPack, Regolith Particle Acquisition and Containment System, where we essentially sandbags, but these are continuous. It's a continuous sandbagging system where you can lay out these long rolls of regolith bagged up, and that becomes your blast shield. Let's go around the pack as well. So those are the elements of the things you need to bring to the lunar surface, which is a lot. It's a lot of mass there, right? So here is kind of the basic construction process, what we call the concept of operations. Succinctly is you move the top layer of regolith, you level the pad area, you lay down the bricks, the underlayment, sorry, you tamp it down, then you lay the bricks from the center out possibly, and then you construct the blast shield. Those are really the basic part of what this is saying here. And what we have here, we have in the green, the delivery elements. You have to, you deliver the equipment to the moon, you have to move it from where you deliver it to where you're going to make the pad to. So those are some traverses and robotics and mobility that has to be into the system. And then you start it up. Now you begin the preparation part of it. This is the excavation and the level and all the ready in the site for the placement of the bricks, which is gathering the regolith, and then you screen it. You can go, another part of it goes to the RegoPacks to get that stuff filled up. And you deliver it to the robot, the filling bot. You transfer it to the furnace, you melt it, you place the nozzle where you want to put it, you fill the nozzle, you regular solidify it, you lift it, and you repeat the process. Now, all that also requires site power, communications, and equipment shelter. So all the things that have to be considered in terms of this concept of operations, and the engineering goes into that in terms of the energy you need to have, for example, the comm links, the data links, and bandwidth you need to have. All right. So here's just kind of a notional, not really a timeline, but just kind of a sequence of when these elements come into play. When if you go from left to right, you have your compactors, you got your haulers. This again, this is just more of a previous chart saying when they come into play in terms of a typical timeline. Not really a good chart. I'm going to change that chart. All right, here's the implication of the communication system. All these elements all have to communicate to each other. They need to talk to each other in some way. There's no GPS on the moon. We have to have positioning and navigation on board on the robots themselves. They need to know where they are in space and time, so they can communicate with the next robot or another robot. And because we're designing these systems, these tools, the interchangeable tools, to be smart tools, so they know when it's time to replace a worn out shovel or worn out hauler of some sort, and know where it's at to go get to it as well. So these are smart tools, and they have to communicate back to Earth as well to understand what, so we can understand what's going on. This is all autonomous. It's all autonomously operated. And so there's the comm system involved in that. And then you have to deal with the power system. Okay, how much power are you going to need to have? This is a tremendous amount of power. Where's that power coming from? We've done some calculations on that in terms of how much power at 100% capacity versus 50% capacity. And for each one of those processes, what are the power requirements needed for that? If you have to have lighting there, okay, if we decide that we're going to work through the lunar night, for example, or do we hibernate for those 2 weeks and put the equipment into hibernation mode, safe mode, and wait for the sun to come back in 2 weeks. That's a big design trait, because if you want to work through the night, you have to design those elements, those equipment for surviving the lunar night, surviving those cold temperatures. Does that make sense economically? To lose 2 weeks of time or whatever, you know, if you're at the equator building these things, versus the cost of building more robust elements into your systems. That's a big more economically decision than anything else. So those are the decisions. But in any event, if we have to work in the night, then we'll need lighting, and that lighting capacity is much. You can see the difference there between 250 kilowatts to 120 kilowatts with light, without light. And so that's a lot of power, intense activity. And in the end, I think it's going to end up being that we need a nuclear reactor up there, nuclear power to serve to power the system up. Because it's not just going to be for the landing pad assembly; it'll be for the other construction that's going to happen as well, the habitats and whatnot. Okay, so here is what we've been doing here locally at the university here in our test bed. This test bed is located on campus. It's over one of the greenhouses by the civil engineering laboratory. It's a 10-foot by 20-foot lunar terrain test bed. We filled it up with our LCAT simulant, and this is a senior design project that was happening to happen last year, and is ongoing this year with a new team. And they were able to show, that we can compact the fluffy, certain amount of soil to some depth, and now they're looking at what happened here with the big lesson learned is that you can see the distance they got. Well, it stopped right there. It's as far as they got with it. That's because all the dust flew up. It got caught up in all the gears and the drive shaft, and it froze up. So the dust is a big issue. We have to design these systems to withstand the dust movement and lofting and the ability to cover up our gears and whatnot. So the next team is looking at that and designing a little bit better way to do that. So we like to take these projects, and especially in the design effort, give them to one team to start off, and if there's looks promising, we'll fund the next level, the next team to continue the development. Who's familiar with what's called TRL, technology readiness level? Okay, see 1 or 2. So technology readiness level is what NASA uses to assess the stage of development that the technology is at. It starts from 0 to 10. 0 is just a basic phenomenon observed. 2 is it's kind of like we've gotten into the lab, and this it's not really a proof of concept, but there's something there. And then 3 is a little bit of a proof of concept. 4, you start doing breadboard and brass board, bench press testing. And then 5, you actually have a little bit of a prototype developed and shows it out. And then 6, you get to testing it into an operational environment, a similar environment like the vacuum chamber, or up in the space station. And 7, you have actually tested it in the actual environment it's working at. And then by the time you get to 8, 9, 10, you're into an operation into a flight hardware. So what we want to do is take these projects and advance that technology readiness level from one level to the next. One team can't do it in one shot. We like the teams to take on the project from one and hand it off essentially, and continue the development of it. That's what we've done. It's been successful with 2 so far. We have one where we were measuring the dust lofting on this lunar surface. We wanted to understand how, when you disturb the surface, how far the dust lofts, and how much, what's the rate of accumulation that it will accumulate on maybe a solar array or on some sort of machinery. And we have devised a little instrument with a technology called QCM, or quartz crystal microbalance. It's in the palm of your hand. It's only about less than a kilogram. And it's gone. It actually began with one of the middle school projects. It's gone from middle school up to now at the graduate level. It's ready to go into flight hardware development at this point. I don't have a picture of it here right now, but we're trying to get that little device on the lunar surface. We're looking to get it funded and put on a lunar lander to test out on the moon. And looking for those. We proposed to NASA those those ideas. So this is actual real projects that are happening. We're not talking about fluffy stuff here. We're talking about you getting involved in a way that you actually have some real game into the real meat in the game, basically. Okay, so what's next here? I think this is just more of the same. Just shows you what we're so we have a license from NASA. This one here, the excavator, it's called Razor. The Razor is a NASA developed tool excavator that I think there's a video here or not. Yeah, let's see if this is play. Nope, I'm not going to play. That's too bad. If you Google Razor, you'll see the way it moves. It's got these two drums on it. One rolls one way and grabs up the dirt, and then when he lifts up, it rolls counterclockwise and dumps it back into the dumper as well. There's two of them on both sides. Anyway, we have this license from NASA to commercialize this, turn this into a way to how do we use this on not only on space but on Earth as well. We want to use these technologies, dual use technologies, so that they have application for our needs here on Earth and solve our problems here on Earth, for whatever it could be. We think this could be useful for terrestrial mining here, or for environmental remediation, where you need to go in there and put a robot in there and dig up bad contaminated soil, or underwater you're doing sea sifting of sands and whatnot. So that's where our goal is there for this one, is to commercialize this, but also get it flight ready for the lunar surface applications. I wish I could show that video. I don't know why, when you go on a foreign computer, it always screws you up. All right, I think I talked about this already. Now it's stuck again. There we go. Yeah, I think I already talked about this. This was just more pictures of the roller. You can see here that how it got stuck into the material, and somewhere there's here's the depth. Here's how far it comes. There was the depth of the regolith, and when they come good 4 to 5 inches of compaction they got. It's a vibrating rotating drum, and it was built here, built there at your machine shop, in your maker shop. Now we have to also start testing these things into somewhat of another environment, a simulated environment. We have a proposal or goal to make one of these a test bed, a lunar terrain test bed that's 10 meters by 1 meter deep. We were trying to get that funded with a program called Lester. We didn't get that awarded, but we're still going forward with another way to do it. So you're going to be seeing hopefully here in San Antonio, this lunar terrain test bed. We're located at Port San Antonio. You're familiar with Port San Antonio? Down there at the tech center. That's where we're located at. We're going to got some approval to go forward with the project to make a large test bed facility and maybe more. So the idea, though, is that it requires 140 tons of regolith, 140 tons of this stuff. You got to deliver that. And this layout here is actually a very specific layout plan that NASA dictated that we needed to have in terms of where the rocks had to be and where the craters had to be. And that is then we would go in there with those little tools, those robots, and then excavate it out and practice the landing pad construction. So here's the idea of what we think we're going to look like. We want to put it there at the port within 3 domes and show it. You can see here the mobility units, the seabird. Here's the excavator, the Razor excavator. There's the roller over here. They've got to go around and they got to interchange. Now, the challenge is how do these robots know when to change itself out? We want one robot to be interchangeable with these tools and know where it's at, where it's been left at before, and how does it do that? What's that connection device? That's a big challenge right there. That's one of the things. And by the way, this Razor, I mean, we're going to be working here at the university to help us develop this Razor. But so the idea is to make this test bed, not only just for research, but for the public to access as well. So we have an ability for the community to be involved with the research, and we'll know what's going on in San Antonio in space construction. Our goal with Astroport is to make San Antonio known as a space construction community. Make that niche for us in the space exploration field. There's more concept designs that be under some domes. So that was our first initial project proposal, was to put these under these 3 domes, where we'd have the test bed and the regular preparation site. That's what we're doing in processing. Maybe we'll want to change out the bed and turn it into a Mars test bed at some point, or maybe we need to change out the material and change out the simulant to another kind of simulant to see if it's a Highland simulant versus a Ferrari simulant. Those are the kind of things that's why that's important to have. And then we need to have the clean room, essentially, to continue to work on the robots and test them out and more on the bench test environment, advance them. But and then we want the dome to be able to mimic the lunar night or the lunar shadows. So it's going to have some intense lighting so that because shadows are big, pretty dark. When you get in the shadow on the lunar surface, it's a shadow. It's dark. Okay, even the temperature changes. So we need to understand that in terms of lighting for vision, for machine vision technologies. And then I mentioned the need for for public access and show it. But this is turned into a bigger project, by the way. So we went and made this proposal to the port, and they said, "That's great, but bigger is a bigger rock. They want a bigger building. They want a bigger research center over there, bigger application." So now we're kind of not back to square zero. We're back to what are those bigger requirements, and we're looking at how that. And we're just getting ready to get that started, figure that out. And then so here's our technology roadmap. We started in 2020. Astroport was founded in March of 2020. We've been able to show that we can prove out the idea of it. We're going to deliver this prototype. We're going to have this. Here's our vacuum chamber. We're putting the furnace into by June of this year. We're supposed to deliver the prototype, and then our next phase is go to the test bed, get the test bed built up, and start doing the testing on the robots to place them down. And then our goal, immediate goal here, major milestone, is to be on the lunar surface by 2026. So NASA has a program called CLIPS, Commercial Lunar Service Provider. They've given awards to about maybe 10, maybe even 12 different companies that are building lunar landers, small lunar landers that will provide 200 kilograms to 500 kilograms of payload. And anybody can get it, if you have the money, anybody can get on those landers to deliver science payloads or engineering payloads for whatever purpose you have. And NASA will fund some of those payloads, but it's a commercial service. And we want to get our melter on the lunar surface to make the first brick on the moon, first bricks on the moon. Can you imagine that? The first man-made structure on a foreign body. And then any of you have enough money, we're going to charge you the naming rights for that brick. Etch it into the laser. All right, so that's the goal there, where we're trying to get to. And I think that's it. That's about the end of it there.